Hello, everyone. This is Jennifer Wu, and I'm a PhD student at Drexel University, working under the mentorship of Professor Savides. In this presentation, I'm going to talk about our work, variation-aware analog circuit sizing with classifier chains for MLCAD 2021. This is the outline of this presentation. I will first go through the background and motivation of this research, and then I will discuss our primary objectives. Then I will dig into the sizing methodology in detail, followed by the simulation results of applying the sizing methodology to the design of an LNA. Finally, I will provide some conclusions. So the first, background and motivation. Shown to the right is a standard analog synthesis flow. So in the schematic level, before we go to the physical synthesis, normally we would have to formulate the design specifications. And after we select the topology, we have to size the components so that the circuit delivers the target performance. Therefore, component sizing is a critical step after selection of the circuit topology. And in most cases, the design specifications can be drastically different for different target applications. As an example, in some situations, we would have target a low power application, while in other cases, we would go for higher performance, like higher gain bandwidth product, and so on and so forth. So really, analog circuit sizing has to adjust for the different specifications to be successful. So motivation of this research includes 3 parts. So we know that analog circuit sizing requires significant domain expertise. Therefore, the automation of the sizing is necessary. There are also additional challenges to account for the effects of process and environmental variations on circuit performance. So we know during the fabrication of the circuit, there are transistor mismatches caused by the process variations. And after the chip is fabricated, the circuit will operate under different environmental circumstances. So those will also have an impact on the circuit performance. And during the design phase, we want to account for these effects. We want to minimize the effects of these variations, therefore making the circuit robust. And the third part is that in existing sizing techniques, there is a lack of modeling of the interdependencies among the performance parameters. And in this work, we show that by including the modeling of the interdependencies of the output parameters, we're able to improve the prediction accuracy, therefore improving the sizing flow. So the primary objectives of this research is threefold. First, we want to develop an automated simulation-based analog circuit sizing flow that is driven by specifications. And this is done by adaptively setting the labeling thresholds with classification. And secondly, we want to model the output interdependencies by applying classifier chains. And thirdly, we want to make the sizing flow variation aware. We do so by including additional constraints on the performance fluctuations of the circuit across all corners. So next, I will talk about the sizing methodology that we propose. So previously, we had another paper also published in MLCAD 2020 that proposes the classification with adaptively labeling thresholds. The key idea is to apply classification to predict whether a candidate solution satisfies the specification. And to handle the class imbalance problem, we propose adaptively setting the labeling thresholds. So the class imbalance problem is a common problem that we will encounter when dealing with the circuit data. So, in the design space, when we randomly sample a data set, the data set will be extremely imbalanced because there will be fewer points that will directly meet your target specifications, while most of them are more or less below the specifications. So with the initial data set, our approach deals with the classification labeling threshold, set that threshold to be the minimum of the design specification and a certain percentile of the target metric in data set when the design specification is a lower bound. And for the design specification as an upper bound, it's the other way around. It's a max of the design specification and that certain percentile of the target metric in the data set. So in this work, we propose a VC-CALT framework, which is developed based on the CALT framework with two primary modifications. The first is that we apply the classifier chain to replace individual classifiers that was initially optimizing each circuit performance parameter independently. So the second part of the primary modification is that we include the constraints to guarantee the robustness of the design solutions to variations. First, the classifier chains. In CALT, we apply individual classifiers to learn a mapping from the input design variables to the output performance parameters. While in VC-CALT, we instead apply classifier chains to learn a mapping not only from the input design variables to the output performance parameters, but also characterizing the relationship among output performance parameters themselves. So we can see to the left of the bottom graph, we have mappings from the design space X to say 4 output performance parameters. They are done independently. And with the new VC-CALT framework, we have not only this mapping from the X to Y, but also the interdependency modeling among the Ys. And finally, we apply the ensemble of classifier chains to further boost the model accuracy. The second part of the VC-CALT modification is that including constraints that guarantee robustness of the design solutions. So we sample an initial data set with performance evaluations at all corners of interest. This includes process corners, temperature corners, and other corners if the user or designer wants to include, such as the voltage corners or aging. So in addition to training classifiers to predict for performance, we also train additional classifiers to predict whether a candidate solution provides robustness to variation. The standard deviation of the variation in the performance of the circuit across all corners is less than a set threshold. This is our basically explicit formulation of how the robustness is predicted. On this slide, it shows the design flow of our framework. We adopted an optimization-based active querying to search for solutions that maximize the output probability scores of all classifiers. Simultaneously, to guarantee the specification and robustness are satisfied. So in the red boxes, we can see the main differences compared with the previous CAD framework. We have to assign labels for robustness, and we will chain assemble classifier chains. Next, I will show the simulation results of applying the sizing methodology to the design of an LNA. So this is a differential common source low noise amplifier in 65 nanometer technology. And we formulate the design constraints to be in this list. We have transistor widths, and inductor and capacitor sizes, and also biasing voltages. So the transistor lengths are set to minimum, and the transistor widths are the range of the transistor widths are set by the PDK. So the corners of interest in this case, in our example, include constraints for robustness formed by the combinations of 5 process corners and 3 temperature corners. And in addition to the performance specifications, we have robustness specifications that basically says that, for example, for the gain, we not only want the gain at the typical case to be larger than 10 dB, but also the across all corners, the variation characterized by the standard deviation is less than 1 dB, which of course we can interpret it to be a robust design solution. On this slide, we see the distribution of the standard deviations of the performance fluctuations across the 15 corners in the initial data set. So we had an initial data set of 1,000 data points. So for example, in the top left graph, we have a gain distribution. The x-axis shows the standard deviation. And so basically, no matter what the gain is, the standard deviation, there are around 300 data points out of the 1,000 data points that satisfy the robustness specification that if we want to, make it to be less than 1 dB. And everything falling to the right side of the plot will be solutions that are not robust to variations, which have large variations. Therefore, without accounting for robustness, the design solutions will have large variation in the circuit performance across different corners. So we apply the classifiers to predict and select robust candidate solutions. The thresholds on the standard deviations are set by the designer, which is again shows the customized feature of this sizing methodology. So suppose the black-red boxes show the range that we want the design solution to be. So they not only have to satisfy the performance specifications, but also within this range. So those solutions, even they satisfy the performance specification, but they fall to the right side of this plot, will not be considered as a good solution and will not be chosen. So here's a summary of the results for the design of the LNA with VCCALT. And qualified solutions are generated that satisfy both the performance and robustness specifications. We can see that the gain standard deviation is 0.74 dB, less than the 1 dB that we set, and the same for the rest of the standard deviation of the performance parameters. And we need 15 times more samples compared with the CALT for simulation of all corner cases. So nominally, it's basically 1,462 set of candidate solutions, but they have to be verified at 15 corners, which makes the number of samples 21,930 points. And it only takes 5 iterations to complete. On this slide, we see the improvement in the prediction accuracy with ensemble of classified chains. So to the bottom left graph, you can see that subset of the individual classified chains outperform the independent classifiers compared with the baseline. So the best classified chain, chain 5, provides a 10.5% improvement in F1 score over the baseline. And we also see that the ensemble of classified chains improves the overall model performance while maintaining the generalization capability. The ensemble provides 3% improvement in F1 score over baseline, as shown by the green bar. So the bottom right diagram shows the example of a classified chain among the ensemble that provides a better performance than the baseline. So we can see that the noise figure classifier is placed at the end of the chain. We can expect that the noise figure predictor is the least accurate, and the data set provides the least information, so that the classifier doesn't want it to misguide the rest of the prediction, so it places at the final stage of the chain. While power, on the other hand, is the most accurate predictor, and it's placed at the front of the chain. So for example, for the gain classifier at the fourth stage, it uses not only the the design variables as the prediction features, but also the predictions from the power, the IP3 robustness prediction, and also the IP3 classifier prediction outputs as features. So the gain prediction will rely on the prediction of those. So we can see that the classifier chain has this feature of propagating that error along the chain. Therefore, we want to place the most accurate and most confident classifier at the front. And it is verified by the result that we basically check the F1 score of each classifier, and it turns out that the power is the most accurate classifier. Next, on the conclusions, we in this work we present a framework called VC-Celt that is variation-aware sizing classifiers to predict robustness. And we achieved improved prediction accuracy by applying classified chains. The ensemble provides 2% improvement in F1 score over independent classifiers. And we also successfully completed the sizing of the components of the LNA for both target performance and robustness specifications. The characterization of the final sized LNA is shown below. And that wraps up our presentation for MLCAD 2021. And thank you for listening to our presentation. If you have any questions, you can email us or ask us directly at the workshop. Thank you.